Hi, one of the basic questions about a buck converter is how we choose the capacitor. In order to know the answer, we need to evaluate the relationship between capacitance and output voltage ripple. So this is the target for this video. So let's start with the analysis. As in the case of previous videos, we are going to do some considerations, some simplifications. Some of them already appeared in those videos. So for instance, we are going to consider ideal components. We are going to consider steady state conditions of our buck converter. And we are going to consider that the inductance is not an infinite value. So as we saw in the previous video, the inductor current has a DC component and then we have some ripple. And the new point is that the capacitance is not an infinite value. In previous videos, we said that the capacitance was very high. As a result, the voltage ripple in the capacitors was zero, and we could say that the voltage across the capacitors is quite constant. But this is not valid for today because in fact, today we want to evaluate the output voltage ripple. We want to evaluate the ripple in a capacitor. So we cannot do this simplification. In any case, I want to point out that this simplification is very close to the reality, because in the reality, when we do a DC to DC converter, we want to have a very constant output voltage. So we will choose the capacitance in a way that the ripple is negligible. Okay, so it's close to the reality, but today we cannot do this approximation because, as I said, the target is to evaluate the ripple in order to have a criteria to choose the capacitance. Okay, first point to see, what is the capacitor current waveform? Well, as in other cases, we are going to consider this node. Here we have three current waveforms: the inductor current, capacitor current, and output current. We already know that the inductor current is something like this. We have an average value, we have a triangular shape, we have some ripple, and the period is the switching period. And today we are going to highlight 3 points that we already talked about that in previous videos, but are important for the analysis we have to do. First point is that if we apply Kirchhoff current law in that node, we can say that part of the current, part of the inductor current flows through the capacitor and another part flows through the load. This is the first point. Second point, the output voltage is quite constant. We know that we have some ripple, but in practice it's quite constant. So we do a simplification here. We assume that the output current is constant. Okay? We already considered that in the previous video. And the third point is that since we are in steady state conditions, the average current through the capacitor must be zero. Well, so if you think about these 3 points, you can conclude that the current through the capacitor is something like this. Basically, what we have is a pure AC current. If you see, the inductor current has a DC component and an AC component. The DC part flows through the load and the AC part flows through the capacitor. Basically, if you manipulate these 3 expressions, you can say that the capacitor current is the inductor current minus the average current through the inductor. Okay? So, conclusion. The current that we have through the capacitor is the AC part of the inductor current. And I want to point out one parameter here. is the peak value, the maximum value of that current, which essentially is half the peak-to-peak inductor current ripple. Well, we will use this in a couple of minutes. Okay, so now we know the current waveform we have through the capacitor. Let's try to use this information to estimate the output voltage ripple. Well, first of all, in the output voltage, we know that we have a DC component. Okay, it's the most important part of the output voltage. And well, we saw in previous videos that the output voltage is duty cycle times VI. Okay, well, actually it's the DC component of the output voltage, but as I said, this is the general let's say result that we see when people talk about the output voltage. Okay, we assume that is constant, and as we saw is this expression. So now, since we have some current ripple in the capacitor, we will have some voltage variations. They are very small, but we are going to study here. So in order to see those variations, we are going to remember the general expression of the capacitor voltage as a function of the capacitor current is this one. As you can see, the capacitor voltage is an initial value plus 1 over the capacitance integral of the capacitor current. Well, if we analyze this expression, we can conclude two things. First of all is if the capacitor current is positive, the voltage across the capacitor rises. Basically, if you analyze the expression, if the capacitor current is positive, you are doing the integral of a positive quantity, and as a result, the value of the voltage across the capacitor rises. And in the second case, if the capacitor current is negative, you are doing the integral of a negative quantity, the voltage across the capacitor falls. So, in summary, we have to see if the capacitor current is positive or is negative. In this way, we can estimate when the voltage across the capacitor rises and when the voltage across the capacitor falls. So, for instance, here we can define that this instant is D1. Here, the capacitor current becomes positive, and as a result, we know that the voltage across the capacitor will rise, and will rise until this point, T2. Okay, so what we know is that between T1 and T2, the voltage across the capacitor rises because the capacitor current is positive. For instance, after T2, the voltage falls because the capacitor current is negative, and it will fall until T3. Okay, so now we can try to draw the output voltage. Will be something like this. As you can see, between T1 and T2, the voltage rises, and between T2 and T3, the voltage falls. Okay, in this case, we don't want to know the specific or the particular shape of the waveform. The important parameter is the output voltage ripple, which is the parameter or design specification that we have to satisfy. So what we need to know is the peak-to-peak output voltage ripple. And as you can see, it can be evaluated as the voltage change between T1 and T2. Okay? So in other words, we are going to see what is the increase of the voltage between T1 and T2. In this way, we can use the expression we have on the slide and say that the capacitor voltage ripple or output voltage ripple is 1 over C times integral between T1, T2 of the capacitor current. And basically, when we do an integral, we are evaluating an area. In this case, we are evaluating this area because we are considering the integral of the capacitor current between T1 and T2 because it's the interval in which we know that the voltage across the capacitor rises. That area is the area of a triangle, so it's very easy to solve the expression. So we can put 1 over C and the area of the triangle. 1 over 2 times the base, this. Okay, if you inspect the waveform, you will see that base is half the switching period. And then we have to evaluate this. And we already know that parameter is half the peak-to-peak inductor current ripple. So in this case, as you can see, we already know the expression or the relationship between output voltage ripple and capacitance. So let's use this information to choose the capacitor. Okay, here we have the expression. As you can see, it depends on the period, it depends on the inductor current ripple, it depends on the capacitance. Let's think about the expression. If we increase the capacitance, what we do is that we reduce the output voltage ripple. What happens if we increase the inductance? So if we increase the inductance, what we know from the previous video is that the inductor current ripple falls. So as a result, the output voltage ripple falls. For instance, let's consider the impact of the switching frequency. What happens if we increase the switching frequency? So the result is that the output voltage ripple falls a lot. Why? Because if we, let me change the color, if we increase the switching frequency, we reduce the period. So we reduce the output voltage ripple. But we also reduce the current ripple as we saw in the previous video. So that's why we reduce a lot the output voltage ripple if we increase the switching frequency. But in general, if we know if we know the switching frequency that we have to use, and we choose the inductance according to the explanation of the previous video, which was taking into account the maximum inductor current ripple we want to have in our converter, we only have the capacitance to ensure the output voltage ripple. So basically what we do in practice is we evaluate this expression. I will use the switching frequency instead of the period because, well, I prefer to work in this way. So basically we evaluate this expression where we have the inductor current ripple that we previously set with the inductance and the switching frequency. We already know the switching frequency that we use, and we will have to satisfy a requirement of output voltage ripple as we previously saw. Perhaps the ripple that we can have in the output is 5 millivolts, so here you put 5 millivolts. And then you evaluate this, you will get a value of a capacitance, and you can choose this value or a higher value to ensure that you satisfy the condition. Okay, but when we have to choose a capacitor, we need the capacitance and we also need the voltage that that capacitor is going to block. Okay, basically is the voltage rating. Why? Because if we have a buck converter, the voltage across the capacitor is the output voltage. So in practice, we choose a capacitor whose voltage rating is higher than the output voltage, but close to that value. We don't choose a much higher voltage rating. Basically, because if you do that, you will penalize the size of the converter, of the circuit. As in the case of the inductance, a capacitor is an element that stores energy. The size of that capacitor depends on the amount of energy that capacitor is able to store. Okay? The energy stored by a capacitor is 1/2 capacitance times voltage to the power of 2. If you increase the voltage rating of your capacitor, means that you increase the amount of energy that capacitor is able to store. So you increase the size. So that's why we choose a capacitor with a voltage rating close to the voltage is going to block in the circuit. For instance, if the output voltage is 5, you want to choose a capacitor able to block 7, 10 volts, perhaps 20, but we don't choose a capacitor of 400 volts, because the amount of energy that this capacitor is able to store is much higher than the one that you need in your circuit, and you penalize a lot the size of the topology. So as an example, here I have a very small capacitor. The capacitance is, I think, that 2 or 3 microfarads, and this one is another capacitor with a very similar capacitance, but the size, as you can see, is much higher. It's because the voltage rating here is 6 times the voltage rating here, and as a consequence, this capacitor is able to store 36 times the energy that this capacitor is able to store. Okay, why 36? Because the voltage rating is 6 times this one. So 6 times 6 is 36. So as a result, the size is much higher here. Well, so with this, we finish with the scope of this video. We have seen how we choose the capacitor. We take into account the capacitance that we need and the voltage we have to block. We have seen also the relationship between capacitance and output voltage ripple. So as I said at the beginning of the video, this is one of the ideas that we need to study when we see a buck converter for the first time. We still need to answer some basic questions before we finish this list of basic ideas about the buck converter. So thank you for watching this video, and see you in the future. Bye.